Now that we've scratched the surface with talking about how do we represent vectors, let's move on to applying that to generate what we call our standard form equation. Or in other words, let's take a 4-bar and break it down into two dyads, or left and right side of the mechanism, and then represent those with vectors and then create vector loops around those. We use this then for synthesis, and we'll use it throughout the entire course. So let me start off with just an arbitrary 4-bar. And I've got a precision point that I'll call P1 in this case. It would go to P2, P3, and so on. And now instead of just having locations from a ground pivot up to a moving pivot, I'm going to represent those with vectors. So on the left side of my mechanism, I'm going to have the W vector and the Z vector, and we'll use that nomenclature throughout, where the link connected to ground is the W vector, the link going from the moving pivot up to the precision point is the Z vector. And then on the other side of my mechanism, that might have been the A side that we were talking about before. On the other side, which we previously talked about as the B side when we did this graphically, I would have the W star and the Z star. You might see this as the U and the S depending on what book you pick up, but in our textbook it's the W star and the Z star. So I've got this in its first position. I can then say, well, what happens when I go to my second position and displace the entire mechanism? So I'm moving this mechanism now to a second position, and I have then displacement of all of these vectors, or rotation of them. So my W vector becomes W prime, my Z vector becomes Z prime, and same thing with the star vectors. The other thing that I have is a displacement vector, which I call delta 2 in this case, from first position to the second one. So that's that green vector that I drew, and we always reference back to the first position. So if I had a third position, I would be going from P1 to P3. So that's our delta 2 vector. Now, what we're going to want to do is to start to form vector loops around this and use that for synthesis. I'm going to focus just on the W and the Z vectors and then the W prime, Z prime. I'm going to forget about the star vectors for now, because we're going to find out that once we figure it out for one half of the mechanism, the other dyad ends up being identical. So once we can solve it for one side, we can solve it for the rest. So let me focus on the left side of this. The other piece I needed to add here was also what are the rotation angles. So my W vector rotates by the angle beta. First position to the second one would be beta 2. My Z vector and my Z star in this case, because they're both part of the same coupler, will rotate by the angle alpha, alpha 2 in this case, first to the second. And then we have gamma is the rotation of the W star vector. All right, so let me focus on just the left side of this mechanism. So I threw away the right side, the W star and the Z star, and now I'm just focusing on the W and Z. Now, the other thing that you'll have to note is that I went from measuring the coupler angle from the bottom of the coupler that went from the two moving pivots, and now I'm measuring this from what is the initial location of, if I'm going from the Z vector right here, I'm drawing these two lines saying that I have a line that's parallel to that, that's this line right here, and now I'm measuring the alpha angle as rotation of that. But remember that because both Z and Z star are part of the coupler, they're going to rotate together, so they're going to have the same alpha angle in all cases. And again, I'm always going to reference back to this first position. So if I'm referencing back to this first position and I use my polar notation, I can express the W prime vector as just a rotation of the W vector, where I have W now being multiplied by its rotation operator, e to the I beta 2. And I can do the same thing for the Z vector, or the Z prime vector, where Z prime is Z e to the I alpha 2. So I take that information and now I create a vector loop equation. My loop equation is basically going to add up all these vectors in a loop. I'm going to start off at the ground pivot right here. I'm going to move up the W prime vector. I'm going to then keep going up to precision point P2, up the Z prime vector. I'm then going to subtract the delta 2 vector, subtract the Z vector, subtract the W vector to get me back to the origin, which is 0. So let me go ahead and write that out, where W prime and Z prime, I'm just substituting in their, how I'd formulated those with the rotation operators. And now what you'll see is that I have a few terms that are similar. I've got W and I've got Z, so I can collect those terms and rewrite this, and I'm also going to put the displacement vector to the delta 2 vector on the other side of the equation. So when I do this, I form what we call the standard form equation, where I've got W being multiplied by e to the I beta 2 minus 1, and then plus Z being multiplied by e to the I alpha 2 minus 1, and then that's equal to the displacement vector delta 2. We're going to use this standard form equation over and over again, and we're going to use it not just for 2 precision positions like I have here, but we're going to use it for 3 and for 4 and for 5, and because of that, we can put it into a generic form where I'm talking about to the j'th position. So not just second position, this could be, J could be the third position or the fourth position, but in every case we always reference back to the first position. So all of my beta and alpha angles and my displacement vectors are always measured from the first position, the W and the Z, when we go through this. All right, so I've done it for the left side of the mechanism, and I said, let's not worry about the right side for now. Well, let's start talking about it now. So just like I had for the left side of the mechanism, I have this same set of equations, or the same vector loop equation in the standard form for the right side of the mechanism, where I've got the W star and the Z star. The only difference is now I'm rotating my W star vector by the angle gamma 2, or gamma instead of beta. I have the same rotation angle for my coupler for Z star as I did for Z, and I've got the same displacement vector. All right, so once we got this, now we're going to use this standard form to synthesize all of our different tasks. So let's talk about what these tasks are and what the prescribed variables are for each one of these tasks. So in motion generation, remember in motion generation I'm concerned about not only a point moving through space, but how much does it rotate? So this was like the kayak or the canoe loading mechanism, where I was concerned about not only where is it located, but what's its orientation. So in that case, my prescribed variables, I would have what's the first position, what's the second position. I described that with the displacement vector, so I would have the deltas. And then I would also have how much does the coupler rotate, and these would be the alpha angles. And this could be, you know, alpha 2 and alpha 3 if I had 3 positions, or maybe even alpha 4 if I went to 4 positions. Path generation, if I add prescribed timing. So path generation, we're concerned about a point moving through space. This would be something like that oil well pumping mechanism, where I've got a pivot there and I'm only concerned about where's that point. I don't care about what the orientation of my coupler is. And in that case, I would have the displacement vectors, the deltas. And then if I'm adding prescribed timing, this is prescribing how much does my input link rotate from the first position to the second, first to the third. So those would be my beta angles. And then finally, when I go to a function generator, now I don't care where my precision point is, but I do care about what is the rotation of the input link relative to the rotation of the output link. So in this case, I'm prescribing both the betas as well as the gamma angles. So we're going to find that once I'm able to specify or figure out what is prescribed as part of the problem, I'm going to then use this standard form to start synthesizing motion generators, path generators with and without timing, as well as function generators. So we'll get to all of those and then extend this out to multiple loop mechanisms as well.